Okay. Okay, and well, in the last lecture, we stopped at the introduction about the design procedures. We actually have introduced the features of different drainage layers and the pipes, which will be applied for the construction of the drainage layers for the pavement. And actually, in the design of the drainage layer, we have to consider two steps. The first thing is like we need to calculate the inflow rate of the waters entering the pavement, and then we need to select the appropriate materials for the drainage layer and the appropriate pipes to remove the water from the pavement structure. So this indicates that we need to know the method to calculate the inflow. And actually, in the for most of the pavement design, there will be three types of the inflows. That will be the surface infiltration, the groundwater seepage, and the meltwater from the ice links. Usually, among all these three sources, the surface infiltration from the rainfalls will be the most important factor we have to consider. For the groundwater seepage, usually that was caused by the low water table during the construction. And the last one, the meltwater, it's usually related to the low temperature, and we have to consider the impact of the frost heave. Only in those regions with the frost heave, we need to calculate the amount of the meltwaters. So those will be the three types of the inflow we have to calculate. And then let's first see how we can calculate the surface infiltration. And usually the surface infiltration is determined by the precipitation rate in that region. And this is related to the weather conditions or the climate conditions in the region where you want to conduct the pavement design. And we actually have one equation to calculate the infiltration rate, which we use the variable Qi to represent the infiltration. And the Qi is actually a function of several variables. That would be the IC, which would be the usually related to the coefficient of the water entering the cracks to the low pavement layers. NC is the number of the longitudinal cracks. This one is actually related to the width of the pavement structure and also to the number of lanes. And WC is the length of the transverse cracks or the joints where the water can easily enter the lower pavement layers. And the CS is the spacing of the transverse cracks or the joints. And also it has a last factor, Kp, which would be the rate of the infiltration through the uncracked pavement surface. This is usually related to the aggregates applied for the different type of the pavement layers. The waters can enter the pavement structure through the cracks. It can also enter through the smooth pavement surface. But of course, usually the value of Kp would be much smaller than the first component of the infiltration rate. So with that, we will usually consider the first component for the calculation of the surface infiltration. We also have the simplified equation to do the estimation. In the simplification, we assume that the NC would be the value of n plus 1, and n is the number of the traffic lanes. Also, we usually assume that the width of the cracks, WC, will be the same to the width of the pavement. So we'll assume these two values are the same. And as I just mentioned previously, in this simplification, we assume that the infiltration from the pavement structure is very small, and then we're gonna ignore it. And then usually for the IC, that will be the crack infiltration rate. In the simplification, we can assume this is a constant value, that is 0.1 cubic feet per hour per feet. And if we put all these assumptions together, you can find out the simplified model as the inflow rate Q, which will be the product of infiltration rate times the width of the pavement, Qi times WP. That will be 0.1 times m plus 1 plus WP divided by CS. And here CS is the spacing of the joints for the concrete pavement. And usually we assume that this is 40 feet for the asphalt pavements. And that's the surface infiltration. And then let's see, check one example to see how we can calculate the surface infiltration. This is the figure that we were using for most of the examples in this under this topic. It's in a two-lane pavement and has the width of 24 feet, and the joint spacing is 15 feet. And we want to find out the amount of the surface infiltration, which means that we want to find out the value of Qi. And with that, let's see how we can do the how we can get the value. So first of all, from the problem, we can get the number of the lanes. The number of lanes is 2. We have 2 lanes, and we also know the width of the pavement. The width of pavement is 24 feet. And at last, we know the spacing of the joints. That is 15 feet. Just a moment, let me. Okay, and we want to find out the value of the surface infiltration. So that is Qi. Okay, to do that, we will recall the simplified formula. So in the solution, we have Q. From the simplified equation, we have Q equal to 0.1 times m plus 1 plus WP divided by CS. So we can apply all the values we get. N equal to 2, WP is 24, and CS is 15. So with that, we have the value of Q as 0.1 times 2 plus 1 plus 24 divided by 15, which will give you the value as 0.46 cubic feet per hour per feet. And we also know that there's a relationship between the inflow rate and the infiltration rate. Here you have to know that the inflow rate and infiltration rate are different. So we know that Q equal to the inflow rate, Q equal to Qi times WP. So Qi is the infiltration rate, which is the value we want to calculate. So with that, finally, we can get the value of Qi as Q divided by WP. So that is 0.46 divided by the value of WP, that is 24. So we have the result as 0.0192 square feet, or we say that cubic feet per hour per square feet. So that's the value of the surface infiltration for this example. So this is the first component of the inflow, which is the surface infiltration. And the second one we have to consider is the groundwater seepage. So this was usually caused by the water entering from the groundwater table, and we also have a very simple equation to calculate the inflow from the groundwater table. And this calculation can be divided into two parts. One is the inflow above the drainage layer. The other one is the inflow behind the drainage layer. So let's go to see the first one. The first one, Q1, will equal to K times H minus H0 square divided by 2 times Li. And you can actually find out the definitions of all the variables. In this equation, K is the permeability of the soil in the cut slope, which would be some the materials or the soils next to the pavement structure, or it will be someone in the subgrade. The second one, a capital H. Capital H represents the initial height of the groundwater table, which would be the water table under the ground before you do the pavement, or before you cut the ground to construct the pavement. And H0 represents the distance, the vertical distance between the bottom of the drainage layer and the impervious layers, which would be the usually we consider the rock of the ground. And also Li is actually in the relation, is a function of the H and H0, and it's the distance of the influence, which means that how large we or how long we should consider about the impact of the groundwater to the drainage layer. So we actually have all the detailed explanation in this page. Usually Li is a linear function of H and H0. That will be 3.8 times H minus H0. So this is one simple equation for us to calculate the inflow about the drainage layer. And we also have a function to calculate the inflow below the drainage layer. Here we're only talking about the groundwater seepage. And usually for the inflow below the drainage layer, we do not have any equation to do the estimation. We usually have some empirical data to find out the relationship between the this kind of inflow below with respect to the width of the pavement structure and the height of the water table, the groundwater table. And actually, you can use the figure on the right to find out the value. The horizontal axis would be the Li plus 0.5 times W divided by H0. And the vertical axis represents the value of K times H minus H0 divided by 2 times Q2. So if you are provided with the value of Li plus 0.5 times W divided by H0, which will be the values you can observe from the design of the pavement structure, you can then go to check the another value, that is W divided by H0. You use this value to identify which line you're going to use in this graph. And then based on the value of the any value you find in the horizontal axis and the line you specified For example, if you specify the value of W divided by H0 is 0.2, then you have to choose this line. And if you find the value of horizontal axis with the value of 0.2 or 2.0, then you probably will get the value of the K times H minus H0 divided by 2 times QA, as in this case, that will be 1.4. And with that, you are able to find out the value of Q2 if we are provided with the value of K, H, and H0. And once you have the inflow about the drainage layer Q1 and inflow behind the drainage layer Q2, you can find out the lateral flow for the entire pavement structure, or for the entire drainage layer. So here, W is the width of the road, including the shoulder. So this is the these two components gives you the calculation of the groundwater seepage, where we can also calculate the lateral flow. And in addition, we can actually calculate the groundwater inflow to the drainage layer per unit area as the 2 times Q2 divided by W. This is for the inflow rate per unit area. And if this pavement is super elevated, which means that it's sloped to one side of the edge, and the collector pipes are installed only on that side, then the lateral flow inflow per unit length of the pipe could be estimated as QL, that is 2 times Q1 plus Q2. And you can also calculate the groundwater inflow to the drainage layer per unit area as QG equal to Q1 plus 2 times Q2 divided by W. And this is only applied to the pavement structure that is sloped to one side. And the equation here is actually applied to the crown structure, which means that the pavement structure is you have the slope to both sides of the pavement structure. And this would be the equations for us to calculate the groundwater seepage. And then let's go back to the previous example to see how we can calculate the longitudinal drain, and also the groundwater inflow rate. So in this we will consider the native soil with the permeability of 0.32 per day, and we want to find out the inflow of QL and the value of QG to the drainage layer. And of course, you have the information, all the information about the pavement structure. You know the width of the pavement as 24 feet. You know the height of the initial groundwater table as 25 feet. You know the vertical distance of the bottom of the drainage layer to the impervious boundary H0 as 20 feet. And we can use this information to complete the calculation, the estimation of the inflow QL and the groundwater inflow rate QG. Also, you know that for this pavement structure, it's actually sloped to one side, and we have the slope as equal to 0.02. And with that, let's go to see how we can calculate the these two values, QL and QG. As this pavement structure is sloped to one side, we will need to recall the two equations defined previously for the super elevated pavement structure. We have QL equal to 2 times Q1 plus Q2 and QG equal to Q1 plus 2 times Q2 divided by W. And this problem wants us to find out these two values. So in the solution, we will first need to find out the value of Q1, and of course, after that we need to find out the value of Q2. So first of all, from the figure of the pavement structure, we can know that the value of capital H is 25 feet, and H0 is 20 feet. And then we will need these two values to find out the variable Li. Is anyone able to tell me how we can calculate the Li? Any ideas about it? We actually mentioned the formulas previously. Okay. So let me just show this formula quickly. So we have Li equal to 3.8 is a linear function of H and H0. Capital H minus H0. And with that, we have 3.8 times H is 25 and H0 is 20, which will give us the value as 19 feet. So the distance or influence is 19 feet. And then the calculation of the Q1 would be very simple. We have the well-defined equation to calculate Q1. Q1 actually equals to K times H minus H0 square divided by 2 times Li. And here K is the permeability of the drainage layer. So we have the of this natural soil. So we have the value of K as 0.34. With that, we will have the value of Q1 as 0.34 times H is 25 minus H0 20 square divided by 2 times 19. So we have the inflow about the drainage layer as 0.22 cubic feet per day per feet. So that's the first one, Q1. And then we need to calculate the value of Q2. So for Q2, we don't have any equation to calculate the Q2 directly, but we can recall the graph that we introduced. Here. We can use the graph to find out the value of Q2. But with that, we need to know the value of the x-axis, which line we have to calculate, and then we can find out the point at the vertical axis. With that, we can calculate Q2. So let me show you the details to do this calculation. So first, for the x-axis, which would be Li plus 0.5 times W divided by H0. And here, W is the width of the road. In this case, we know WP is 24, and we also know the width of the shoulder, which would be 10 feet on each side. So with that, we can know the width of the road as 10 plus 24 plus 10. That is 44 feet. So this is the total width of the road. And with that, we can easily calculate the value for the x-axis. So for x-axis, we have the Li is 19, and the width of the road is 44, and H0 is 20. So we get the value as 2.05. So that's the value for the x-axis. And then we need to determine which line we're going to use. So with that, we need to calculate the value of h of the w divided by h0. So w is 44, h0 is 20, and with that we get the value as 2.4, and we need to use this one to find out which line. With that, let's go to the next page, the graph that we're going to use. For the x-axis, we can find out the value we calculated previously is 2.05, which would be someplace around here. 2.05. We cannot get the exact value. This is just some approximation. It's reasonable for you to get some errors here. And for the line is determined by the value of w divided by h0, and what we calculated is 2.2. We do not have any specific line in this graph to show the value of 2.2, but you can find out some similar value between draw a similar line by yourself between 2.0 and 4.0. This is a line for the between 2.0 and 3.0. This is 2.0, this is 3.0. So there might exist a line between 2.0 and 3.0, but it's close to 2.0. And with that, we can find out the value of the vertical axis. I actually have, with that, you will find out the value is around 0.74. This is the value we get from the graph, based on the value from the x-axis and the line that is determined by w divided by h0. By combining these two values, we can then find out the value of the y-axis, and we know that expression of y-axis is k times h minus h0 divided by 2 times q2, which we get the value is 0.74. So we know the value of k, we know the value of h, which means that we can easily find out the value of q2. So q2 equal to k times h minus h0 divided by 2 times 0.74. So k is a 0.34, that is the permeability, times 25 minus 20 divided by 2 times 0.74, which will give you the value as 1.15 cubic feet per day per feet. And now, is anyone able to tell me what's the value of QL and what's the value of QG? Do you know how to get the value? Any ideas about it? Okay, so basically we can recall the definitions of the QL and QG for the sloped for the sloped pavement structure, which is a slope to one side. We have QL equal to 2 times Q1 plus Q2. And in this case, we know that Q1 is 0.22 and the Q2 is 1.15. So we get the QL as 2.74 cubic feet per day per feet. And QG, that will be Q1 plus 2 times Q2 divided by W, that will be the width of the road. So we have the value as 0.22 plus 2 times 1.15 divided by 44. So the result is 0.057 cubic feet per day per feet square. So that's the procedure for us to calculate the value of the inflow rate of the groundwater seepage. And here you can see that for the same example, we have QI, the infiltration rate, it's 0.46, and this one is much larger than the groundwater seepage. And that's the reason we have to consider that the infiltration as the most important component of the inflow for the pavement structure. So that's the second component, groundwater seepage. And do you have any questions so far about the inflow rate calculation? If not, then I will go to the third component about the third component about the meltwater. And this one, let me try to disable that. Okay. So the meltwater is also an important component for the inflow to the pavement structure, especially at some cold regions, and and we have to consider the meltwater during the freeze and thaw cycles. And actually, we have analyzed the first heave impact to the pavement structure, and this one is also related to the meltwater. Usually in the calculation of the meltwater flow rate, we will consider the rate QM as the function of three variables, which is which would be the average rate of the heave. This is related to the type of the soils, and also the regions that we have to where we will do the pavement design, and the permeability of the subgrade soil, and the consolidation pressure on the subgrade. And these three variables will be used for us to identify the meltwater inflow rate, which is usually represented the average inflow rate during the first day after the thawing to the day that all the ice lanes are melt. And usually this figure actually shows the relationship between the average rate of the heave with respect to the meltwater inflow rate, which would be the QM. Basically, you can see that with the higher value of the permeability, that would be the K. The meltwater, if we are provided with the same same average rate of the heave and the same value of the consolidation pressure. The meltwater inflow rate is also higher, and also if we increase the value of the consolidation pressure, we will also find out the inflow rate will be larger, which will be related to the value in the x-axis. And this figure actually shows each line will represent one consolidation pressure. And we're going to use this one to determine the value of QM by giving the average rate of the heave, the consolidation pressure, and the permeability of the subgrade soil. So those for the, as we know that in this calculation there will be three variables. We know the how to find out the permeability, and it's also easy for us to calculate the consolidation pressure depending on the width or the thickness of the upper layers about the subgrade. But the average rate of the heave is very hard for us to estimate. So usually we are using some empirical data to estimate the heave rate, and the heave rate is highly related to the type of the soils, and the also the percentage of the particles passing 0.02 millimeter sieve, and which would be the portion of the fine particles. And this table actually shows the heave rate with respect to different portion of the fine particles for the soils defined by the USCS method. For example, if you have the percentage passing 0.02 millimeter sieve as 0.4%, then the heave rate is usually around 3 millimeter per day. And you can find out the other values, for example, for the sand and the gravel sand, if the percentage is between 1 to 2%, then the heave rate is 0.8. And so on. We're going to cite this table to identify the heave rate based on the grain size distribution. And here I will show you one example about the calculation of the meltwater inflow rate. So here in this example, we are considering the COD sand subgrade, and it has 9% particles which can pass in number of 0.02 millimeter sieve, and also it's subject to the frost action. We want to find out the value of the inflow rate, QM. And in this example, we assume that the weight of the concrete is 150 PCF and 115 PCF for the drainage layer. So this is actually in the pavement structure with the PCC and then the drainage layer. And this is the subgrade. We also know that the this is for the example in the previous lecture, the thickness of the PCC slab is set as 9 inches. And the drainage layer is 6 inches. So with that, we want to find out the value of QM. So first of all, let's go to check the value of, in the solution, we first need to find out the value of sigma P, which would be the consolidation pressure. If we are given the the density of the PCC slabs and the density of the drainage layer, you can calculate sigma P as 150 times the width the thickness of each layer. So you remember here you have to convert this thickness to to feet. So for the PCC layer, 9 inches would be 9 times 12, 9 divided by 12 feet. And for the drainage layer, that is 6 divided by 12 feet. And with that, we can find out the sigma P as 170 PCF. So that's the first one. And the second one is the first heave, the average rate of the heave. Here we know that the percentage of the fine particles is 9%. So if we go back to the table here, for 9%, which would be the soil of SM, and if the percentage passing through 0.02 millimeter sieve is 9 to 22%, then the rate is between 9.0 and 5.5. And we will consider the same boundaries for the low boundaries that will be 9%, which will represent the heave rate of 9 millimeter per day. So with that, we have the heave rate as 9 millimeter per day. And then we can use the figure on the right to calculate the melt inflow rate. So first, we know that sigma P is 170, which means that you need to find out a line between 100. So here you don't have any line about 170, so you need to find out an approximate line. So this one is 100, this one is 200, this is 150. So we have some line in between. I did not draw this one very well, but you just know that there's someone in between. It will roughly parallel to the line on the left and line on the right. And for the heave rate, that would be the 9. So you can find out the value here. And with that, you can then find out the value of the x-axis, which is around 0.74. So we have with that we have the x-axis, which is a qm divided by the square root of k as a 0.74. This is from the graph. And with that, qm will be 0.74 times the square root of k. K is the permeability, that is 0.34. So finally, we found out the value of qm as 0.43 cubic feet per day per feet square. So this is the value from the meltwater. And so with that, we have introduced all the three sources of the inflow, the surface infiltration, the groundwater seepage, and the meltwater. In the drainage design, we have to summarize all the three sources. And also, we need to minus the outflow through the subgrade soil. But usually in the design, the outflow is related to the permeability of the soil on the water table at the boundary of the pavement structure. And this value is usually very small, so we can ignore that. If we ignore the outflow, we can simplify the calculation of the design inflow for the drainage layer. So if there's no flow, so the design can actually be divided into two conditions. If there isn't any frost action, the design inflow will be QI plus QG. Well, we don't consider the inflow from the meltwater. We only consider the surface infiltration and the groundwater seepage. And if there's any groundwater flow, then it will be even simpler. The design inflow will just be the surface infiltration. And if we consider that there's some frost action, then here we have to include both surface infiltration and meltwater. And actually at this part, we can ignore the inflow from the meltwater, because usually the meltwater, from seepage, usually ground seepage is much smaller than the other two sources. So with that, I can quickly go through one example. Say that we have the calculation of the previous three sources of the inflows. Then let's see how we can find out the design inflow. We know that QI equal to 0.46 and QG equal to 0.057 and QM equal to 0.43. Also, we have the value of Q1 equal to 0.24. So if there's any no frost action, then the design inflow will be QI plus QG. So that is 0.46 plus 0.057. So we have the value as 0.517 cubic feet per day per feet square. And also we can find out the case if there's some frost action. Then we have the QD equal to QI plus QM. So the result is 0.46 plus 0.43. So we have the value as 0.89 cubic feet per day per square feet. Well, so that's the way for us to calculate the cubic infill rate and to find out the design inflow for the drainage layer. And I think we were done for the lecture today. In the next lecture, I will try to finish the rest component about how to select the materials for the drainage layer and how we can select the pipes to satisfy the design inflow. I think that will be all. Do you have any questions so far? Okay, if we don't have any questions, I guess that'll be all about lecture today. And just feel free to let me know if you have any additional questions, send me email or send me direct message through Teams. And also I have uploaded the second homework assignment. You will have enough materials to work on the second homework. Feel free to let me know or email the TA if you have any questions about the assignment. Okay, I think that will be all today. If you don't have any questions, I will close the meeting day. And I really appreciate your attendance to the class. If there's no question, I will see you on Wednesday.